Now let's talk about what to do if you have two qualitative variables. In this case, you can make an investigation if these two variables associate. What is association? Association, actually, it's any relationship between two variables. So you can think about, for example, we already know such statistics as covariance and correlation, which we use to find the association between two quantitative variables. In this lecture, in this video, we will talk about how to do the same, how to find similar statistics, but for the qualitative variables. Okay. So the two variables are associated if we change one variable, if any change in one variable leads to change in the second variable. So for the qualitative data, it means that if, for example, one proportion will get higher, what happened to the proportions for the other variables? For example, if we talk about the proportions, salary proportions for those engineers who know R and for those engineers who don't know R, will they be the same, or actually knowledge of R will increase the, for example, proportion for getting high salary, or vice versa, it will decrease it? That's the sort of association we can use for the qualitative variables. Okay, so how to find the association? First of all, we need to learn how to represent the qualitative data if we have two variables and we would like to know any association between them. In this case, we will use contingency table. So the idea of contingency table is following. Take every level, every separate level for one variable, and then calculate proportions for the second variable. So for each, for example, level in knowledge of R variable, we calculate the proportions for the salary, or we can do it vice versa. These proportions are also called observed frequencies. So let's learn how to calculate them. Okay. So that's how any contingency table looks like. You have, for example, this is the first variable, this is the second variable, and these are all levels for the variable. So for example, if you have 3 levels in one variable and 2 levels in the second variable, you will have 3 by 2 or 2 by 3 table with 6 levels, right? And then you calculate the total. You just sum up the levels in the rows, and then you sum up the levels, the values in the columns. Okay. So let's do that. So we have 2 levels for the knowledge of R, and we have 3 levels of the salary. So that's how the contingency table looks like. Okay. So what it tells us? It tells us that, for example, 7 engineers who don't know R have low salary, and 5 engineers who know R have also low salary. Okay. 17 engineers who don't know R have average salary, and only 7 engineers who know R have average salary. Then we have also the same for high salary. So 6 engineers who don't know R have high salary, and 8 engineers who don't know R, have high salary. Then we have the proportions for every level. So in this case, these are engineers. How many engineers don't know R? How many engineers know R? And then we have these proportions for the salaries, for the low salary, for the average, and for the high salary. And that's the total amount of values, total amount of answers in our data. Okay, so that's how contingency table looks like, and this is the most important part of it. Okay, that's actually the observed frequencies. Now let's learn how to find out the association, how to estimate if there is any association between the variables. So we assume that our null hypothesis is that no association at all, as usual, right? Null hypothesis means no effect. So we assume that there is no association between variables. Then we compare 2 sets of frequencies. The observed frequencies, it's the table we just calculated, we just computed. And then we also calculate expected frequency. Expected frequency is how these values in the contingency table should look like in ideal world where we have no random influence. Okay, so we just calculate if indeed there is no association between the variables. How many, for example, engineers who know R will have small salary, and how many engineers who don't know R will have small salary. So these are expected frequencies. And then we just calculate, we investigate how far the observed frequencies are from the expected frequencies. Is this difference between observed frequencies and expected frequencies is extreme enough to reject null hypothesis? So that's the basic idea. Now let's learn how to do that. So let's start with the calculating expected frequencies. So we already know the observed frequencies for our case. Now think. The proportion for engineers who know R and who don't know R at 0.6 and 0.4, right? 0.6 don't know R, and then 0.4 know R, right? Now we can think, so 12 engineers in total have low salary. How many of them should don't know R, and how many of them should know R? Well, apparently, if there is no association, that's the split, right? So 60% and 40%. So that will be our expected frequency. So we calculate it using just these 2 proportions. So these are expected frequencies, right? And then if you compare the real frequencies and expected frequencies, you can see they're pretty close to each other. So you can see we have 7 here and 7.2 here. We have 5 here and 4.8 here. So it's not that far, right? Now we can do the same for the average. Again, we know the proportions for the variable knowledge of R. And then we can know that we have 24 engineers in total with average salary. So again, 60% of these engineers, of these 24 engineers, don't know R, and the 40% should know R. So we calculate expected frequencies similarly. And now we can see that actually we have some difference, right? So we have 17 here, but 14.4 here. We have 7 here and 9.6 here. So we have some difference in this case. Is it significant or not? We don't know now. We don't know yet. Okay. Then we calculate the expected frequencies for the third case. Again, we have 14 engineers in total with high salary. 60% of these 14 don't know R, and 40% of these 14 should know R if we don't have any randomness. And null hypothesis is true. There is no association between these two variables. So we calculated the expected frequencies, and just look, now we also have a difference. We have only 6 here, but 8.4 here. We have 8 here and 5.6 here. So apparently the expected and observed frequencies are different in our case. But is it significant different? How likely we can get this difference if indeed there is no association between the variables? Let's calculate that. Okay. So the idea is following. Let's take a difference for every combination of levels. Let's take a difference between the observed and the expected. For example, 7 minus 7.2, 5 minus 4.8, and so on. And then look, this difference can be negative, can be positive. But we are interested only in absolute values, right? So let's square this difference and standardize them. Okay. So that's the way to do it. We just take a difference, square it, and then divide it to the expected frequency. Okay, so this is the statistics we calculate for every combination. Then if we do the calculations, that's the values we get. Okay, so you can see that we have the squared difference between the two values, and it's standardized, right? So that's the differences. That's the differences. And then we just accumulate all these differences together. So we have a sum of squared differences, and that's the value. This is sum of squared differences. Okay. Now, let's recall the block number 2. We already know a distribution that describes a sum of squared values taken from the normal standardized distribution, right? It's a chi-square distribution. So we can use chi-square distribution to find out if this value is extreme enough for being taken from the population where there is no difference. Okay. So this statistic is called the chi-square statistic. So in this case, it looks like this. Okay. And in this case, it's always positive because it's a sum of squared values, and it depends on degrees of freedom. In this case, the degrees of freedom, it's number of levels in the one variable -1, and number of levels in the second variable -1. Okay. And then we can use a chi-square distribution, a CDF function for chi-square distribution, to calculate a p-value, right? And then we have 3 rows and 2 columns, so we have 3 levels in the first variable and 2 levels in the second variable. So that's the degrees of freedom. So it's 2 degrees of freedom. And what you see here is the chi-square, chi-square distribution for 2 degrees of freedom. And that's the value we've got. Okay, so this one, 2.9, that's our statistic. Then you remember that, I mean, if you think about extremeness, what will be more extreme in this case for null hypothesis? Null hypothesis assume there is no difference. So it means that the only statistic which is not extreme for null hypothesis is 0, right? But the larger differences are the bigger chi-square difference, the bigger chi-square statistics will be. So the extremeness, the direction of extremeness is this one, right? So it means that the p-value, it's a right tail for the given statistics. So that's the chance to get a sample as extreme as ours and more extreme. Okay. So if we calculate the p-value in this case, we will get 0.23. So 23% chance to get a sample as extreme as ours, or even more extreme for null hypothesis, if indeed it came from the population when null hypothesis is true. Okay, so we don't see an evidence that there is any association between the knowledge of R and the level of salary. Okay, however, if you take a bit bigger sample size, for example, in this case you can see this is the same sample size as we have. And in this case, I got a sample size 150, and I kept all the proportions, all the combinations. For example, you can see if this is 7, this is 21, so it's just 3 times bigger. If this is 5, this is 15, so 3 times bigger. So I kept all the proportions the same. So in this case, if you calculate the chi-square value, it will be about 8.7. So the chi-square statistic will be about 8.7. Again, it will be 3 times larger than the chi-square statistics we have in this case. Okay, and then you can see that the p-value, it's very extreme in this case. The p-value, it's an area on the right tail, so this area. And if we calculate it, we will get about 1%. So if indeed we made this experiment, we asked 150 engineers, randomly pick it up, and got these values, got these answers. 1% chance to get these values, to get these differences, if actually there is no association between the knowledge of R and salary. And it seems to be extreme. So in this case, we would assume that indeed there is association, the knowledge of R influence the salary level.